you know that without engineering drawings, Western civilization as we know it probably would not exist? And the reason for this is virtually every manufactured part was made with the use of engineering drawings. Engineering drawing is the technical language by which we can communicate very precisely size and shape information about parts. And so every part or every machine that's making a part requires many engineering drawings. Let me show you a couple examples of engineering drawings. Some examples from my archives from when I was a kid just starting in this business. But I just want to give you an idea what we mean when we're talking about mechanical drawings or engineering drawings. I was digging through my archives the other day and I uncovered this drawing. This is actually a drawing that I made when I was 19 or 20 years old and working at Bell Telephone Laboratories in New Jersey. And in those days, this was exciting for me. This drawing might not look exciting to you, but what it was part of the electronics chassis that was used to control the Telstar satellite, which was the very first communication satellite. Now this is just a front view with leaders and words that show which parts are put into this electronics assembly. Let me show you a copy of what we call a detail drawing that shows how this chassis or the base part of this assembly was drawn. Now this drawing is a lot bigger than we have room for in this little television set right now, but if we zoom out on the whole drawing, you won't be able to read anything. This is actually a drawing of the sheet metal chassis, and you notice that not only is the shape described by this picture, but the size is described with these dimensions. If I show you over here on the right side view, you can see that this is made of sheet metal, has this nice little hook here, and the front cover actually latched around that so that it would be very clean on the front, and we only needed fasteners on the back. Let me show you another couple of examples from my past. Now this goes back again to the early 1960s, but I was working for a hydraulic filter manufacturer. In this case, we have an assembly of a small hydraulic filter that was actually used on aircraft to clean the oil as it flowed through some of the hydraulic systems. And probably can't see on the TV screen, but there's actually something called a lock wire. The point is that every single tiny detail of every part must be clearly communicated. And the way we communicate it is through engineering drawings. In this case, we have an assembly drawing and it shows how all the parts are put together. If we want to know how to make one of these parts, I can show you this drawing. And this is the detail drawing. And there are lots and lots of dimensions and lots of little symbols that tell the machinist how smooth this has to be, where to put the holes, what angles to put. In any case, this kind of drawing is required for every single part that's to be manufactured. And without a complete set of engineering drawings, we could not make very many things. Would be back in the days of the craftsmen who are using our little whittling knives or our axes to carve things out of wood. And we certainly wouldn't have all the wonderful tools and toys we have to play with in this time in history. When people first decided that they needed to communicate technical information very accurately, they had a philosophical issue to deal with. We live in a three-dimensional world. But the engineering drawings typically exist in two dimensions, either on a two-dimensional piece of paper, like in the examples I showed, or more often nowadays on a two-dimensional computer display. The question is, how can we describe completely a three-dimensional world on a two-dimensional surface? Let me show you some of the ways that have been invented to project three-dimensional objects onto two-dimensional media. In this presentation, I'll review some of the traditional methods of projection. There are four basic ways to show three-dimensional objects on two-dimensional surfaces. We have what's called perspective projection, we have isometric projection, oblique projection, and orthographic projection. Let's start out with an example from the world. And here I've shown on the screen a photograph of a large European cathedral. Now, even though this photograph is being displayed on a two-dimensional screen, you get the feeling that there is a third dimension here. And the reason for that is something called perspective. The way perspective works is that The farther away things are from the viewer, the smaller they appear. And we can actually make drawings that utilize perspective to give the illusion of 3 dimensions on a 2-dimensional media. Here's a very famous architectural example by the architect Frank Lloyd Wright. This happens to be a photograph, but it illustrates perspective. Notice how as you go farther into the picture, I'm saying go into the picture, and you feel that you're going into the picture, even though your brain really knows it's a 2D image of the house. But what makes it appear that we're going into the picture is that as you move into the picture from things that are near to places that are far, things appear to be smaller. All of the lines that in real life are horizontal all seem to be going towards the same point, and this is called a vanishing point. Notice that if we trace these lines, they all converge at a point here to the right, and also the lines that are parallel at a 90-degree angle to those appear to converge off the display here at a second vanishing point. If this was a picture of a skyscraper that was very tall, these vertical lines would also appear to converge at a third vanishing point. Now imagine that you wanted to make a drawing that used this idea of perspective. Perspective has been used by famous artists for hundreds of years, but it's difficult to do. It's difficult to do because as things are farther from the viewer, they're different sizes. Even though in reality, one end of this wall is the same height as the other end, in the perspective image, it's a different size. So to construct these, you need to have a constantly changing scale. And there are techniques used to do this, but they're very inefficient with regard to time. Well, there's another way to project 3-dimensional objects onto 2D media to make them easier to view without all the complexity of constructing these changing scale perspective drawings. And that method is called isometric projection. Here again, you see all 3 dimensions of the object in a single view. But in this case, the parallel lines are drawn parallel. And iso means equal, metric means measure, and when we construct this isometric projection, we measure all these distances equally, the width, the height, and the depth of the object. The nice thing about isometric projection is that it's close enough to what we see with our human eyes that someone who is not trained in engineering drawing can recognize what they're looking at. One thing about isometric projection is that someone with no training in engineering drawing can pretty much understand what they're seeing. It doesn't take a lot of training because this, although it's not exactly what we see when we look with our human eyes, it's not exactly perspective, it is close enough so that average people can understand this. However, it's inadequate for completely showing dimension. One difficulty in constructing isometric projections is when we have circles or cylindrical features or arcs. You'll notice that cylindrical features or arcs appear as ellipses in isometric drawings. This means if you're going to make an isometric drawing, you have to construct this ellipse, which is a little harder than constructing a regular circle. The next type of projection we'll show is called oblique projection. In oblique projection, we see all 3 dimensions of the object in a single view, but this time we take some surface of the object and draw it true size and shape, and then we project the other dimension back at an angle. If we have a lot of arcs and circles on this true size and shape surface, this makes oblique projection a little easier than isometric projection. However, all 3 of these types of projection, perspective, isometric, and oblique, are inadequate for completely communicating technical information. The problems we get into are when we have things in the views that are hidden away from our sight, or when we need to precisely dimension every feature. So, orthographic projection has been invented. Orthographic projection provides a means of showing all three dimensions with several views, each view containing two of the three dimensions. In this case, we have a front view, we have a top view, and we have a right side view. And this is all constructed on a two-dimensional surface, but it's a three-dimensional object. A little later, I'll show you how we create these orthographic projections. For now, you need to know that the three dimensions all appear in an orthographic projection. However, in any particular view, only two dimensions appear. The front view in this case shows the width and the height. The top view also shows the width and the depth of the object, while the right side view shows the height and the depth of the object. Now, it should be the goal of every engineering drawing student to be able to look at orthographic drawings and to visualize the three-dimensional model in their mind. Can you do that? Can you see this three-dimensional object by studying the top and front and right side views? Do you imagine something like this? Well, that ability only comes with experience, but it's an important ability to develop, and that is to develop the ability to visualize a three-dimensional object by looking at a collection of two-dimensional views. Now remember that we've discussed several standard projection methods: perspective, isometric, oblique, and orthographic projection. All of these methods were developed to be able to describe a three-dimensional world on a two-dimensional media, whether it be drawing paper or computer displays. A little earlier in this presentation, I discussed a little bit about orthographic projection. Now, to help beginners understand how we produce orthographic views using the principles of orthographic projection, teachers for many years have been using something called a projection box. And I've simulated the projection box here through the use of computer graphics. One of the tools that instructors have used over the years to help students build their three-dimensional visualization skills is a glass projection box. Well, I've used some computer graphics here to simulate that projection box to help you see how we create the different orthographic views. Here is a computer model of an object shown inside a glass box. And what we do to create the views is we project an image of that object onto the different surfaces of the box. You'll notice that here I've labeled this H for the horizontal reference plane. We have to think of this top surface of the glass box as a projection plane, and we run many, many lines from the object to that reference plane, and we get an image, a two-dimensional image of the object on the reference plane. This particular reference plane up here that's horizontal is called, appropriately enough, the horizontal reference plane. On this side, we've created a frontal reference plane labeled F. And here we've projected, as we say, we've projected the object or an image of the object onto the front reference plane. And here is a profile reference plane, which results in what you're used to calling the right side view. Some people would call it a profile view. Let's look at this in a little more detail. Now here I've projected the image of the object onto the horizontal reference plane. You should observe that all horizontal surfaces appear true size and true shape when projected onto the horizontal reference plane. We have a profile surface here. You think of it as a vertical surface, but so is this a vertical surface. Remember, we have a profile surface and a frontal surface, but both of those surfaces, when we project them onto the horizontal reference plane, come out lines or edges. Now remember, this is a two-dimensional image of a three-dimensional object, so we have to keep all three dimensions in mind. Let's project this object onto the frontal reference plane. And you see here, we've drawn all these infinitely many, well, I haven't drawn all infinitely many of them, but I've drawn the key projection lines that are perpendicular to the reference plane through every point on the object, and we get the image we call the front view, which is actually the image projected onto a frontal reference plane. Now, if we were looking at the object with our line of sight parallel to those projection lines, some surfaces are hidden from our view, and we represent those surfaces with dashed lines. This object has a hole, and the surface of that hole is actually cylindrical. The way we show that surface, it's going to be hidden now when we're looking in the front reference plane. The way we show that cylindrical surface is to show dashed lines, because it's hidden in this view. We show dashed lines at the limiting elements, or the farthest points over, that hole gets to. That'll actually be a distance equal to the diameter of the hole across. When we project the object onto the profile reference plane, we again see that cylindrical hole as two dashed lines projected onto this surface, onto this reference plane surface. Also, all profile surfaces appear true size and shape when we project them onto the profile reference plane. Horizontal surfaces appear how in the profile reference plane? This is a quiz question. Now, you in the third row over, second seat, what's the answer to this? What do horizontal surfaces appear as when we project them onto a profile reference plane? You're right. They appear as a line, or sometimes we say they appear as an edge. Now, when you get a little more advanced into orthographic projection and you start doing auxiliary views or descriptive geometry problems, it'll be very important to know the distance from the object to a reference plane. Here I've illustrated the distance from this object to the frontal reference plane. Notice that if you're actually looking at the front view, you could not measure that distance because it collapses to a point. However, if you're looking at the top view, you can measure the distance from the object to the front reference plane. What happens to the front reference plane in the top view? It looks like a line. When you see formal descriptive geometry or auxiliary view problems, you'll see this front reference plane labeled F. Whether you're looking at the top view or the right side view, it appears as a line. Again, if you're looking at the right side view, you can measure the distance from the object to the frontal reference plane. If I wanted to carry this a little farther, I could illustrate the distance from the object to the horizontal reference plane or the distance from the object to the profile reference plane. Again, this will become more important later on when you get into auxiliary views. Keep in mind that to construct orthographic views, we actually project images of the object onto these principal reference planes. One technique that we've developed, we instructors of engineering drawing that is, one technique that we've developed over the years to help students build their three-dimensional visualization skills is surface identification. And it is important that you be able to identify the names of the different types of surfaces and that you be able to identify those surfaces in every different orthographic view. Let's take a look at a model here. There are 5 different types of surfaces. They are frontal, horizontal, profile, inclined, and oblique. 3 of these surfaces, the frontal, horizontal, and profile, are considered principal planes. Let me install with computer graphics an object here that we can use to learn about the different surfaces. I've created this computer graphic to illustrate the different types of surfaces. In this graphic, you'll see a top view, a front view, and a right side view. These are the 3 common orthographic projection views, and I've also installed a pictorial to help you identify the different surfaces. Let's start with a frontal surface. The frontal surfaces are always parallel to the front reference plane. Now that does not mean that this object only has one front surface. It actually has 2 frontal surfaces. This one that's shaded and almost its cousin here on the back side. We cannot see it but it's there and it's parallel to this. All frontal surfaces are parallel to the frontal projection plane. Now, try to imagine, try to visualize where this front surface appears in the orthographic views. Can you see it in your mind? In the front view, frontal surfaces always appear true size and shape, but they appear as lines or edges in the right side view and in the top view. Now, one thing you have to keep in mind always, as one of my professors used to say, think 3D thoughts all day. This top view is not just a 2D thing, although it's on a 2D screen. This is an image of a 3D object. And although that surface is collapsed to a single line, keep in mind that that line is representing the entire 3D, in this case frontal, surface. Let's look at another surface. Here is a horizontal surface. Horizontal surfaces are parallel to what you expect horizontal surfaces to be parallel to. In this case, there are several different horizontal surfaces on this model. How many horizontal surfaces can you see? Can you imagine? Well, there's the one that I've shaded here. There's another one that's in the middle, and there's one more. The whole bottom surface of this model is another horizontal surface. Now visualize where this horizontal surface appears in the top, front, and right side views. Can you see it? There it is in the top view, and in the front view it appears as an edge, and in the right side view, again, it appears as an edge. Keep in mind that all horizontal surfaces always appear true size and shape in the top view, and all horizontal surfaces also always appear as edges in the front and side views. Here's another horizontal surface that's been shaded. By now, I hope that you can guess where this one will appear when I shade it in the 3 orthographic views. There it is, true size and shape in the top view, and it shows up as an edge or as a line in the front and in the right side view. Let's look at a profile surface. Profile surfaces are all parallel to the profile reference plane. You might have thought this was the right side view, and you're correct if you thought that. But technically, if you get into the language of descriptive geometry, some people will actually call this the profile projection, because this is the image of the object as projected onto a profile reference plane. And this surface is parallel to that profile reference plane. Can you imagine it in the 3 orthographic views? Here we go. True size and shape in the right side view. Profile surfaces are true size and shape in the profile view. And the profile surface shows up as an edge in the front view and as an edge in the top view. How many profile surfaces are on this block? Quick quiz question for you. Thought you were going to watch this without getting a quiz? You're wrong. Okay, imagine you there in the back row. How many profile surfaces? You're right, 2. The one that I've shaded and the one on the back of the block. We don't see it in this view, but it's there. Now, there are 2 types of surfaces that do not come out true size or shape in any of the principal views. The first type we'll look at is an inclined surface. This surface that I've shaded here in the pictorial is an inclined surface. Can you imagine what this surface looks like in the top, front, and right side views? Well, there's only 2 possible ways a surface can appear. It can either appear as an area or it can appear as an edge. If it appears as an area, it either has to appear true size and shape or it has to be foreshortened. In all cases, whenever a surface appears as an area, it always has the same general shape no matter what view it appears in. In the case of this inclined surface, it appears as an area in the top, and it appears as an area in the right side view, and it appears as an edge in the front view, but in wherever it appears as an area, here in the profile or side view, here in the top view, it's foreshortened. It's not true size and shape. If you were looking straight into that object, perpendicular to the profile reference plane, you would not see this surface true size and shape because it's going away from your eye. Okay, there's one more type of surface to discuss, and that's this little one right here. This surface is not true size and shape in any of the principal views, and it's not an edge in any of the principal views, and we call it an oblique surface. Take a look at where this oblique surface appears in the top, front, and right side views. Oblique surfaces do not appear true size and shape in any of the principal views, nor do they appear as edges in any of the principal views. So there you've seen the different surface types, and it's important for you to be able to look at an object, pick out a surface, and identify what type of surface that is. Keep in mind that we have frontal, horizontal, profile, inclined, and oblique surfaces. Up until this point in my presentations, most of the time I've been showing orthographic drawings that have three views. Actually, the formal system of orthographic projection has 6 principal views. Let me just review briefly the 6 principal views and their appropriate positions relative to each other. We'll start out by building the display with a front view, and then we'll add the top view. Now, in the United States, we use a system called third angle projection, and in that system, the convention is to always put the top view directly above the front view. If you go to some European countries, they use something called first angle projection, and they place the top view in a different location than we do. Actually, if you work on international drawings, sometimes labeled System Internationale, there'll be a little symbol that'll show you whether they're using first or third angle projection. But for the purposes of today's discussion, we're going to concentrate on third angle projection, where we start with the front view, and directly above that, we place the top view. Directly to the right, we position the right side view. Now, this alignment is very important. Notice that the height is measured in both the front and the right side view, and they're directly aligned. The top view holds the width, and the front view shows the width, and they're directly aligned. These are the 3 views you're used to seeing so far, but there are 3 more. There's a left side view. Now, it's a little tough to see on the television screen, but this big horizontal surface that has the hole in it is visible in the right side view. When we look in from the right, we can see it, and we see a solid line there. When we go around the other side to the left and look back at the object, that surface is there, but it's hidden, and so we show it as a dashed line. Notice the difference between the left and the right side views. The next principal view, we'll add the bottom view. This is the same thing we'd see if we were underneath the front view looking back up at it. Would get the bottom view. And when we're looking back up at it, notice that that whole wall there becomes dashed because it's hidden from us. When we're up above looking down, we can see that as a solid line. The 6th view is placed over here, and it's the rear view. If you think about it, if you take a block, an old toy block or a cube, it has 6 faces, and we have a principal view for each of the 6 faces possible on a 3-dimensional block. Let me review one more time which of the 6 principal views show which of the 3 dimensions. The width is shown in the front, top, bottom, and in the rear views. The height is shown in the front, right side, left side, and rear views, while the depth of the object is shown in the top view, the right side view, the bottom view, and the left view. Now, I've spent a lot of years introducing this subject to a lot of students, and every once in a while I have a very bright student who's very creative and decides that they have their own place that they'd like to place views. Well, although this is very creative and very interesting, it's absolutely the wrong thing to do. It would be the same thing as if you invented your own particular spoken language. When you went around and tried to talk to people, no one would understand what you were saying. Well, remember that engineering drawing is the communication language of industry. The only way people will understand your engineering drawings is if you use the same language that everybody else uses. And that is standard orthographic views, the 6 principal views, positioned in these classic locations. The business of engineering drawing is extremely important, especially to the manufacturing industry, because engineering drawing is the language, it's the technical communication language that we use to completely communicate information about the size and shape of objects. In order to understand this communication language, you need to be very familiar with the different ways of projecting three-dimensional objects onto two-dimensional media. You need to know how orthographic views are made. You need to be able to identify different types of surfaces within orthographic views. And hopefully, through this videotape, you are well on your way to understanding and creating engineering drawings.